Hello, and welcome to our lecture, first part of the mole. Now, this is a topic that when you probably first learned it seemed so confusing, but I hope that what you realize is it actually isn't very difficult, okay? The mole is simply a conversion factor, nothing more, all right? You don't need to understand how they developed it, how they discovered it, how they calculated it in the first place. You just got to be able to use it. So the mole is often referred to as Avogadro's number because Avogadro discovered it. The mole is 6.02 times 10 to the 23rd anything. Just like I could say a dozen eggs, a dozen songs, a dozen granola bars, you would know I meant 12. Well, if I say a mole, you know I mean 6.02 times 10 to the 23rd. The reason it seems scary is because it's so big. But it is so big. We're talking microscopic things, all right? And so that's why we need this mole, because it gives us kind of a bridge between something microscopic that we could never even imagine being able to touch or measure, something like a single atom. They're getting there to be able to see them, which is crazy. But so it gives us a macroscopic thing if we convert it using the mole. And he did figure this out based on the number of atoms that's in a 12-gram sample of carbon 12. Just fun fact. So as I mentioned, 1 mole is 6.02 times 10 to the 23rd of anything. In chemistry, we consider it to be 6.02 times 10 to the 23rd representative particles. All a representative particle is the smallest unit in which a substance, an element or a compound, naturally exists. So for pure elements, the very basic subunit is an atom. For an ionic compound, the very basic subunit is called a formula unit. So if we remember, ionic compounds form crystal structures. So there aren't individual little atoms, there aren't individual little molecules. Instead, there's big crystals. So we consider one formula unit its representative particle. So if this were a crystal of sodium chloride, then one formula unit would be a singular sodium and a singular chlorine. That would be one formula unit. And then for molecular or covalent compounds, the single representative particle is a molecule. Another way that we use mole is when we think about molar mass. Now, molar mass is exactly what it sounds like. It is the mass in 1 mole of a representative particle of a substance. So the units are in grams per mole. This is the mass we find on the periodic table. So whatever mass number is listed for an element on the periodic table, that tells you that there is exactly that, or that's exactly how much 1 mole of that would weigh. So if we look at this little picture, for 3 separate things, so like for sodium, if I had 6.02 times 10 to the 23rd atoms of sodium, they would weigh 22.99. But if I had that many atoms of lead, it would weigh 106. That's so weird. This is 207. Oh, I'm looking at palladium. It would weigh 207.2. And then if I had an entire mole, which is 6.02 times 10 to the 23rd atoms of helium, it would have a mass of 4.0. So for all of them, we're talking about the quantity 6.02 times 10 to the 23rd particles. But they have different masses because they have different molar masses. Okay, so again, I mentioned this is just the mass that's listed on the periodic table. If we need to find the molar mass of a compound, we're still going to use the periodic table. We just need to add up all parts of the compound together. So if we have sodium chloride, we look up sodium's mass on the periodic table, 22.99. We look up chlorine's, 35.45, and we add them together to get the whole mass of sodium chloride. Potassium nitrate, we look up potassium, we look up nitrogen, and we look up oxygen, but because there are 3 oxygens, I have to multiply oxygen's mass by 3. And then I'm going to add it all together. So don't forget your subscripts when you're calculating your molar mass. Something that is extremely important to remember because it can trip you up is we have something called diatomic molecules. These 7 atoms or elements do not exist as singular atoms. If you have a sample of pure hydrogen, it is not going to be singular hydrogen atoms. It's going to be hydrogen molecules. Same thing with oxygen. You're not going to have singular oxygen. You're going to have O2. Okay? So for all of these, if they are by themselves in a pure sample, they're going to be diatomic. So their formula is going to be like H2N2O2. We can remember these. We start at number 7, element 7. We make a 7 plus hydrogen. All right. So this is something you want to mark on your periodic table, something to keep in mind. Because if you're asked to find the molar mass of, say, nitrogen gas, if you look up nitrogen on the periodic table, it says 14.01. But pure nitrogen gas is in 2. So the molar mass of nitrogen gas is 2 times 14.01. Or chlorine is 2 times 35.45. It's a typo. Okay, so let's do a couple of practice problems. Like before, I would pause this, do them on your own, and then check your answers. So the first one, sodium hydroxide. What is sodium hydroxide? Naming. I have to be able to write formulas, right? I can't just look up sodium, and I definitely can't look up hydroxide on the periodic table because hydroxide isn't on the periodic table. Its individual atoms are. So sodium hydroxide, the formula is NaOH. Sodium is +1, hydroxide is -1. I'm balanced. So I'm going to look up the mass of sodium, 22.99, plus the mass of oxygen, which is 16, plus the mass of hydrogen is 1.01, and I get 40.0 grams per mole. All right. Oxygen gas, diatomic, its formula is O2. So I look up oxygen, which is 16, so I do 2 times 16, 32.0 grams for every mole of oxygen. Finally, calcium phosphate, Ca3, PO4, 2 is going to be my formula. So I look up calcium, 3 times 40.08 plus, we got to remember to distribute this to each part of the polyatomic ion. So there are 2 phosphoruses, 30.97 plus 8 oxygens. And we multiply that together and add it all up, we get 310.18. Sorry, I'm out of room. 310.1. Okay, so now that we know how to calculate molar mass, we can go into our kind of third conversion. So we've talked about Avogadro's number, 6.02 times 10 to the 23rd. We've talked about molar mass. Now we're going to talk about volume. So the volume of a gas specifically, not of anything. So remember, gases are the only thing that take up the volume of their container. So the volume of a gas at STP. Well, what does STP mean? Standard temperature and pressure. So if this gas is at 0 degrees Celsius or 273 Kelvin and 1 atmosphere, we know that that gas has a volume of 22.4 liters. A little bit later, we're going to talk about the ideal gas law, and I'll explain where that 22.4 comes from. But at this point, you just need to know that 1 mole of any gas at STP is equal to 22.4 liters. So now we have 3 total conversions. All right, we always have the mole right smack dab in the middle. That mole is our common ground. It is what lets us convert in between mass, volume of a gas at STP, and representative particles. Okay, so I can convert in either direction. I can go from mass to mole using the molar mass, or I can go from the mole to mass using the molar mass. I can go from mole to volume, or I can go back from volume to mole, so on and so forth. I can do 1 step, or I can do 2 steps, depending on what the question may ask me. So this is why we reviewed that factor label method or dimensional analysis, because mole conversions is where that comes into play. So let's do a few practice. Again, if you'd like to pause before I work these out so you can try it on your own and then look at the answers. So question 1 says, what is the mass of 5 moles of iron 3 oxide? So just like in any other conversion problem, I'm going to start with my given. So I'm starting with 5 moles of iron 3 oxide, and I want to get to mass. Well, my way to go from moles to mass is with molar mass. So I have to determine the molar mass of iron 3 oxide. That's what we just did in previous slides. So when you do that math, you're going to get 159.7 grams per mole. So I have mole here, so I have to have mole on the bottom. I know that 1 mole of iron 3 oxide is equal to 159.7 grams. How did I know that 159.7 grams? I used my periodic table to calculate the molar mass, what we did prior, right? Okay, so now I'm in grams, which is what the question asked me, so I'm going to multiply these two numbers, and I'm going to get 798.5, but because of 3 sig figs, I'm going to round that to 799 grams of iron 3 oxide. Okay, how many moles are in 1.5 times 10 to the 25 molecules? So this time I'm starting with molecules of water, and I want to go to moles. Well, if I have molecules at the top, I know I have to have molecules at the bottom. Well, what conversion factor do I know with molecules? Oh, I know that there are 6.02 times 10 to the 23rd molecules for every 1 mole. Now I'm in moles, which is what my question asked me for. So I'm going to multiply across the top and divide by the bottom, and I'm going to get 24.9 moles of water. So again, remember, these are conversions. This is the same quantity. 24.9 moles of water and 1.5 times 10 to the 25th molecules of water is the exact same amount of water. We're just converting the unit by which we're representing it in. Okay? What is the volume at STP of 2.8 moles of oxygen gas? So I'm starting with 2.8 moles, and I want to go to volume. What conversion do I have that goes moles to volume? Oh, 22.4. So 1 mole is 22.4 liters. So I'm going to multiply across the top, and I'm going to get 62.72, which I'm going to round to 3 sig figs. So I have 62.7 liters of oxygen gas. So if I asked you to go measure out 2.8 moles of oxygen gas, I don't have a molimeter. I don't have a way to measure moles. But by converting it, you could absolutely go measure out 62.7 liters of oxygen gas. And that's where this mole comes in handy, because it allows us to calculate quantities that are actually measurable. So now let's try some 2-step. So again, pause if you'd like, do these on your own, and then check your answers. What do I mean by 2 steps? I mean In the prior slide, we only had to do one conversion because we were either going to moles or we were coming from moles. Now we're going to have to do 2 steps because now we are either starting with grams, volume, or representative particles. So we're going to have to go through the mole up to the other thing we're converting to. So in this one, oxygen gas fills a container to a volume of 44.8 liters at STP. How many molecules are present? All right, so I'm starting with 44.8 liters, and I want to go to molecules. I have no idea how many liters or how many molecules are in a liter. What I do know, though, is that 22.4 liters equals 1 mole. How did I know to use 22.4 liters? Because my unit here was liters, so I have to have liters down here. And I have to go to a mole because the mole is my thing that's in the middle that allows me to go between liters, grams, or particles. So I know I have to convert to moles. Now I'm in moles, but it wanted molecules. So I know that 1 mole is equal to 6.02 times 10 to the 23rd molecules. Multiply across the top, divide by the bottom, and I'm going to get 1.20 times 10 to the 24th molecules of oxygen gas. Okay, common sense check here, because sometimes we can plug things in funkily, I don't know if that's a word, into our calculator. I was going from liters to molecules. A molecule of oxygen gas is tiny compared to a liter. So my number should have gotten way bigger, which it did. It went to 1.2 times 10 to the 24th. That's like 24 zeros. Okay, so use your common sense and look at your answer for a second and say, does that make sense? All right, next question. Find the molecules in 5.5 grams of nitrogen gas. Okay, so I'm starting with 5.5 grams. Now I know I have to go to a mole, and I have to have grams down here to cancel that out. Well, I don't know about grams in a mole. Molar mass. So I look at the periodic table, and nitrogen is 14.01. But remember, the formula for pure nitrogen is N2. So I have to do 2 times 14.01 to get 28.02. Now this asks me for molecules, so I have to go one further step because I know 1 mole is 6.02 times 10 to the 23rd molecules. And when I multiply across the top, divide by the bottom, I get 1.9 times 10 to the 23rd molecules of N2. Again, common sense. It makes sense that my answer got really big because it's in molecules. Last but not least, what's the volume of 15.6 grams of carbon dioxide? So I'm going from grams to volume. So I have 15.5 grams of CO2. 1 mole of CO2, when I look at my periodic table and calculate the molar mass, is 44 grams. Now my question asked me for volume, so I know 1 mole is 22.4 liters. I'm going to multiply across the top and divide by the bottom, and I'm going to get 7.89 liters of CO2. See? Simple.